for finding C using Rolle's theorem? Next, second example, find C of Lagrange's mean value theorem, LMVT, short form LMVT, for fx is equal to Lx square plus mx plus n in closed interval a comma b. That means I have taken general quadratic polynomial, any interval a comma b. Polynomial function is defined everywhere so that it is continuous as well as its derivative exists. Okay, fx is continuous in closed interval a comma b. What is f dash x? L into x square derivative 2x, m into x derivative 1 plus n derivative constant derivative alone 0. There is derivative standard basic standard formulas you refer. Okay, so if a constant is multiplied with any x term, then that constant derivative will not affect, will come as it easily. Other x terms only affect derivatives through derivatives. Exist in open a comma b. Of course it is exist in closed interval a b, but due to theorems that proves they have invented, that means they have given the condition in open interval a b, it is sufficient. Okay, it is assumed, because some problems are there which are differentiable, not differentiable at endpoints. Okay, next, now what is the formula for finding C? F dash is equal to fb minus fa by b minus a. In f dash x put x is equal to c, that is 2lc plus m. In fx put consecutively successively b and then a, lb square plus mb plus n minus LA square plus MA plus N divided by B minus A. So numerator n cancel. There are two A square terms and there are two L terms and then two M terms. Simplify the like terms. L into B square minus A square can be written as B minus A into B plus A, and then after taking common M into B minus A, so that B minus A is getting common. So this simplifies to L into B plus A plus M. So both sides cancelled, again m first and then L, which implies C simplifies to A plus B by 2. Okay, so this is the arithmetic mean of A and B, which is always lies between their numbers A and B, between A and B. So here I am writing a point, star point, AM, arithmetic mean, geometric mean and harmonic mean of A and B are respectively a plus b by 2 root over ab and 2ab by a plus b. Whatever the mean, always that value so obtained after calculating, taking randomly any two numbers a and b, calculate any mean, that value so obtained lies between a and b. Later you check. Third problem, find C of the Cauchy's mean value theorem for fx is equal to square root x and gx is equal to 1 by square root x in closed interval a comma b, where a greater than 0. So that means the first value in the interval greater than 0, automatically when we are moving on right side, every number is increases in the interval. Interval meaning is like that. Okay, Now square root function are defined for positive integers, positive numbers only. So root x and 1 by root x defined in this interval. Because a is greater than 0, automatically b is greater than a, so b also becomes positive. Or you can write, instead of a greater than 0, this also, b greater than a greater. In some textbooks it is given like that. That means all the numbers in the interval are positive, greater than 0. So I am going to directly finding f dash x. F dash x, square root x derivative 1 by 2 root x, and g dash x derivative minus 1 by 2x times root x. Just convert first of all this into x power n form. X power n notation, derivative is n into x power n minus 1. Simplify, then you will get these two notations. Okay. So whenever the fraction comes into the case, take care about the denominator. Denominator should not be 0. Okay, because we have to show exist. Okay. So here both are not defined at x is equal to 0. But 0 does not belong to the between a and b. Okay, the starting point is already given greater than 0. So both are exist in open a comma b. And what is the third condition? G dash x we have to prove not equal to 0. Yes, when the fraction becomes 0, either numerator 0 or denominator infinity. Numerator is minus 1. Denominator x value is not infinity because x is nothing but any point in the interval or between a and b. Okay. For all x in open a comma b. Now the formula for finding c. F dash c by g dash c is equal to fb minus fa by b minus a. F dash in f dash x g dash put c, and then in this in fx and gx, sorry, here I have written wrong, gb minus ga. So 1 by 2 root c minus 1 by 2c root c, this is equal to root b minus root a by 1 by root b minus 1 by root a. So this simplifies to the second fraction comes to numerator and then reverted here after taking LCM and then revert. It simplifies to LHS simplifies to minus c. In this root b minus root a divided by root a minus root b divided by root b into root a. So this simplifies c is equal to root over ab. What is root over ab? I have given already GM, geometric mean, which is always lies between a and b, that is open interval a comma b. Now I am asking a simple one more question. Later you try that answer. Why it is not applicable? Rolle's theorem cannot be applicable for fx is equal to mod x in minus 1 comma 1 because I want reason. Later you try. One more question. Why this theorem is not applicable? Just recall your basics which I have already given. Now I am going to Taylor series. Taylor's series or Taylor's expansion. Fx is equal to fa plus x minus a divided by 1 factorial f dash a plus x minus a whole square by 2 factorial f double dash a plus so on plus x minus a raised to n divided by n factorial f n a, nth derivative of fx at a, plus so on. This can be written as in summation form sigma n is equal to 0 to infinity x minus a whole power n by n factorial f n a is called Taylor series expansion of fx at x is equal to a or in powers of x minus a. About x is equal to a or in powers. Just underline. Here f of x is continuously differentiable. Putting a is equal to 0, we get f of x is equal to f0 plus x by 1 factorial f dash 0 plus x square by 2 factorial f double dash 0 plus so on x power n by n factorial f nth derivative 0 plus so on is equal to summation n is equal to 0 to infinity x power n by n factorial f nth derivative 0. Comma is called Maclaurin series. Now see, any function satisfying this continuously differentiable, first derivative, second derivative, etc. exists, then this function can be expressed as infinite series expansion as fa plus x minus a by 1 factorial f dash a square, second factorial f double dash a, that is the derivative and the denominator factorial number and the exponent power number all are equal. Nth power n factorial nth derivative. This can be put in summation n is equal to 0 to infinity. This is called general term. Okay, so this is first term. This is second term, this is third term. Please remember, sometimes the question asks find the third term in Taylor's theorem like that. Okay, next is called Taylor series expansion of the given function fx in two types. About x is equal to a, that is in given in terms of about x is equal to a. The Taylor series about x is equal to a is also pronounced as, is also say as in powers of x minus a, which can also be said that about x is equal to a or in powers of x minus a. Okay. Now in this, if you put a is equal to 0, the scientist Maclaurin invented this series, that is just put a is equal to 0, which is called Maclaurin series, which is nothing but Taylor series about origin. Origin means a is equal to 0. 0 is called origin. Origin. Please by heart both Taylor series. The question asked either in this word or in this word, about a point, or other word is Other way of asking, in powers of x minus a. See, each term, this first term also I can write x minus a raised to 0. Each term is containing powers of x minus a. That's why it is called powers of x minus a. Each term, that is function, first derivative, second derivative, are all specified at which number? A. Each function and its derivatives are calculated or specified at which number? Particular a only. That's why this is called about x is equal to a. Now I am giving some standard Maclaurin series expansion which are useful for doing problems in Taylor series. Generally the questions coming in this topic is find the Taylor series. Okay, either some non-zero number or zero number, or the question asks in powers of x or in powers of x minus 5 by 6, like that. The second way, find the third term, find the second term, like that. The third way, find the coefficient of x minus a whole square, find the coefficient of x minus a whole cube, like that. Okay, just observe. So these expansions are valid for some conditions, for some values of x or all values of x. That values of x is called region of convergence. Okay. So due to some values of x or all values of x, depending on the function, this series going to convergent. Okay. That values of x is called region of convergence. Please remember the values of x where the Taylor series or Maclaurin series going to convergent, comma, is called region of convergence. Okay, like that. Note. Now these are the some standard expansions of Maclaurin series. Exponential x is equal to 1 plus x by 1 factorial. This is already given in limits. X square by 3 factorial, x cube by 4 factorial, plus so on. 2. Sin x, x minus x cube by 3 factorial plus x power 5 by 5 factorial minus so on. And sin hx is equal to x plus x cube by 3 factorial plus x power 5 by 5 factorial plus so on. 3. Cos x 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus so on. And cos hx is equal to 1 plus x square by 2 factorial plus x power 4 by 4 factorial plus so on. All these are valid for all x in R. R means real number. For every real number these are going to valid. That means these expansions right side are going to convergent for every x in real number. Convergent means going to some quantity, finite quantity. Divergent means going to infinity or minus infinity. 4. Log 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus so on for minus 1 less than x less than or equal to 1. Just what I am highlighting, underlining, please remember that conditions, the values of x in every series, that is called region of convergence. Because sometimes the questions, this expansion is valid for a minus 1 less than x or x greater than 1 or x less than or equal to 1, like that the questions coming. 5. 1 minus x whole power minus 1. 1 plus x square plus x cube plus so on. 1 minus x whole power minus 2. 1 plus 2x plus 3x square plus 4x cube plus so on. Like that whole power minus 3 not required, etc. These are valid for minus 1 less than x less than 1. And this can be put in the modulus form mod x less than 1. and just write this is also mod x is equal to L implies x is equal to plus or minus L. Mod x less than L, sometimes we have to express in with modulus and without modulus also. X minus L less than x less than L. Mod x greater than L, which implies x less than minus L, comma x greater than L. Just take the number line minus infinity to infinity, randomly select a number L and minus L, collect all the numbers between minus L to L, greater than L, less than minus L. These are the three categories. Comparing with mod x, comparing the mod x with the given number is equal to L, less than L, greater than L. Sometimes expressing without modulus, sometimes expressing with modulus. These are, both sides are equivalent. So please remember by heart these expansions. For every expansion against, I have given some x values, that is called region of convergence. The values of x where these series going to convergence, that is called region of convergence. Please remember, sometimes the questions find the ROC, region of convergence, for the given series. And moreover, you remember M1 paper BTech first year, first semester, I don't remember exactly, some infinite series chapter, convergent, divergent, oscillatory series, alternating series. If you look at that, you know the procedure for saying series is convergent for some x values, that is called region of convergence only. Okay. Now I am giving problems. This is asked in 2000. The Taylor series, I am writing in short form TS. TS means Taylor series. Expansion of sin x about x is equal to pi by 6 is 2 marks given. See, some problems using by one by one term calculating in the RHS of Taylor series standard expansion. That means finding one by one derivative using definition method. Okay. Some problems using direct some note point standard expansions I have given Maclaurin series. All expansions are called in powers of x, some 5 to 6 expansions. Using that standard formulas we will get the final answer. Okay. Solution. So what is, so I am going to do this problem by what I gave, the Taylor series expansion. That means term by term calculating derivative. Taylor series expansion of fx is equal to, what is that, sin x, about x is equal to pi by 6. That is, about x is equal to a is, what is that expansion? Fx is equal to fa plus x minus a by 1 factorial into f dash a plus x minus a whole square by 2 factorial f double dash a, and then etc. Here a is nothing but pi by 6. Now what is fx? Sin x. Go on finding the derivative at least 2 to 3 terms. And then after substituting a value, you should get at least 2 non-zero terms. Depending on the options also, you know where do you stop to finding the derivatives and then substituting the given a. So minus cos x derivative minus sin x, etc. Substitute a value in the in all these. A value pi by 6. Pi by 6 means 30 degrees. Sin 30 value 1 by 2, cos 30 value root 3 by 2. So 1 by 2 f dash pi by 6 root 3 by 2 f double dash pi by 6 minus 1 by 2, etc. So therefore 1 implies. What is 1? Here all of you please say equation 1. What is fx? That is sin x, or you can write simply fx. Fa, that is we got 1 by 2. F dash a root 3 by 2 times x minus a. A means pi by 6, or you can write divide by 1 factorial also. Plus minus into half, that is minus 1 by 2 x minus a whole square, pi by 6 whole square by 2 factorial, and then putting etc. So this problem I have done by 1 calculating the derivative on the RHS of the Taylor series standard expansion. So I am going to show one more problem without this method. That means finding 1 derivatives. Okay. Which is given 2009. The TS expansion of fx is equal to sin x by x minus pi in powers of x minus pi is dash. Solution. So if you go by the previous method, f dash x, f double dash x, at least 2 derivatives, 3 derivatives, and depending on the options, every time you need to find u by v rule. And if you substitute a is equal to, that is here in powers of x minus a, compare your definition so that it gives a is equal to pi. If you put pi, the first term itself it gives 0 by 0, then everywhere you need to find L'Hospital rule, apply L'Hospital rule. So it becomes complicated, the problem becomes laborious. Okay, so in that such cases, see, to expand fx in powers of x minus pi, that is about x is equal to a. Here pi means a. Now see the logic here, without 1 derivative, it takes laborious the method. Now finally what we have to prove, final sentence, in powers of x minus pi means your last step, all the terms containing powers of x minus pi. That means right from the beginning, if possible, wherever it is x, you try to express, try to get x minus pi. Already this is x term which is in the form of x minus pi. This is an x term which is not x minus pi. So to get x minus pi here, subtract pi and then add pi divided by x minus pi. Now it looks like in the form of, if I say this is x minus pi as a new term theta, 180 plus theta which locates in second quadrant sign gives negative. So this simplifies to minus sin x minus pi divided by x minus pi, since sin 180 degrees plus theta is equal to minus sin theta. Okay, now all the terms, now all x terms in the form of x minus pi. So keep outside minus 1 as well as denominator x minus pi, and just comparing this with the sin theta, where x minus pi is equal to theta, I have given sin x expansion. Okay, that means how much? X means here x minus pi whole cube by 3 factorial plus x minus pi whole power 5 by 5 factorial minus, see, since sin theta expansion, theta minus theta cube by 3 factorial plus theta power 5 by 5 factorial minus, so on. Now multiply the outside term with inside terms, that means simplifies to minus 1 plus x minus pi whole square by 3 factorial minus x minus pi whole power 4 by 5 factorial plus so on. If you do the same problem by previous method, calculating one by one derivative, each step becomes 0 by 0 after putting x is equal to pi and then applying L'Hospital rule. Okay, this final answer you will get like that only. So based on these two models, I am giving you one more problem. Later you do at home, which is given 2003, 2 marks. Third problem, the TS expansion of the function fx is equal to x divided by 1 plus x around x is equal to 0. Applying either one by one calculating derivative method, that is first problem, or like this. And you check the answer I am giving correct or not. X minus x square plus x cube minus so on. Later you check the third problem answer. Fourth one, which is given 2012, 2 marks. For the function f of t is equal to e power minus t by tau. Tau is a constant, comma, the TS, the Taylor series expansion for t less than, double less than means it is very much lesser than tau, t much lesser than tau, comma, is dash. The Taylor series not given expansion, sorry, a word approximation. Anyhow, I am giving the options. 1 plus t by tau, 1 minus t by tau, 1 minus t by 2 times tau square, 1 plus t. Solution. Here instead of x variable it is given t variable, e power minus t by tau. Okay. Now since t is much lesser than tau, therefore t by tau much lesser than 1. That means neglecting, this is the reason, very very important, neglecting the square, cubes, etc., which is going to vary approximately to 0, etc. Okay. And what is e power x expansion? 1 plus x by 1 factorial, x square by 2 factorial plus etc. Okay. With the help of these two, here x is nothing but minus t by tau. So this simplifies to 1 plus minus t by tau. Okay, that means approximately equal to 1 minus t by tau plus etc. and then approximately equal to this symbol approximately equal to 1 minus t by tau, because I have neglected due to this reason. So answer is option B. That is the reason. Easy to understand. Take care about these reasons, and then I have written only one step and then put etc. This approximately equal to 1 minus t by 2 because of neglecting squares cubes. Partial derivatives. So generally these cases occurred in the situation more than two independent variables, more than one independent variable. Ordinary derivatives are the derivatives differentiation with respect to exactly one independent variable. If the derivatives are with respect to more than one independent variable, then partiality comes the case. Let u be a function of two independent variables x and y, that is u is equal to f of x comma y comma, then the derivative of u with respect to x, keeping y constant, is called the partial derivative of u with respect to x. Okay, and is denoted by dou u by dou x, or in suffix cases ux. When the suffix indicates here in this partial derivative with respect to x, that is ordinary differentiation only. If once you remember the formulas, basic formulas, just differentiate with respect to x, then keep all other variables constant. Here other variable is y. Okay. Similarly, the derivative of u with respect to y, keeping x constant, comma, is called partial derivative of u with respect to y, and is denoted by dou u by dou y, or some pronounce as del u by del y, or u suffix y. Higher order derivatives, del square u by del x square, dou square u by dou x square is equal to dou by dou x of dou u by dou x, del u by del x, del by del x of this can also be represented in suffix form. Similarly, dou square u by dou y square is equal to dou by dou y of dou u by dou y, del by del y of del u by del y. This can be represented u y y. Here del square u by del x del y, that is dou square u by dou x del y, depending on the region, depending on the look, I mean people pronouncing like that. Okay, some people pronounce as dou, some people pronounce as del. Del by del x of del u by del y, and del square u by del y del x is equal to del by del y of del u by del x. This is also represented u suffix y x. This is represented u suffix xy. Whenever the given dependent variable, that is the function u, has continuous second order partial derivatives, in all ordinary normal cases these dou square u by dou x dou y is equal to dou square u by dou y dou x. Whenever the function u has continuous second order partial derivatives, u xy is equal to u by x. That is del square u by del x del y is equal to del square u by del y del x. And similarly, whenever the u is a function of more than two independent variables, x, y, z, t, etc., same procedure is adopted, keeping all other variables constant and then remaining variable differentiate with respect to that one. Okay. So, similarly, the function is defined for x, y, z, t more than two independent variables. The partial derivative of u with respect to x is defined as the derivative of u with respect to x, ordinary derivative method, keeping all other variables constants. Next, let z be dependent variable, that is a function, and x comma y are independent variables, that is z is a function of x comma y. Then the following notation is adopted for some problems. Okay. Then small p denoted by del z by del x, small q del z by del y, small r alphabetical order easy to remember del square z by del x square, small s del square z by del x del y, and t del square z by del y square. So whenever x and y are independent variables, z or u or function f any other is independent variable, this 5 letters alphabetical order is adopted. Then following notation is adopted for the first and second order partial derivatives p, q, r, s, t. Not only z, suppose f, suppose u. Okay. Except p, q, r, s, t in the given dependent variables. In the given dependent variable, except these p, q, r, s, t. Remaining any variable, you can treat these 5 letters p, q, r, s, t. The notation for first and second order partial derivatives to be used p, q, r, s, t. Okay. Not only z is a dependent variable, f is a dependent variable, u is a dependent variable, any other dependent variable. Okay. This notation is follows generally in problems. Okay. This is useful in maximum minima. Okay, this notation p, q, r, s, t. Okay.